Now let's talk about indexing. Indexing is the process of preparing our knowledge base so that it can be efficiently searched up at the time of query. Let's write it down. It is the process of preparing our knowledge base so that it can be efficiently searched up at the time of query. Let's say we want to prepare the database of our project architecting intelligence. For preparing the database, what I would do is I would upload all the course materials, that is PDFs, PPTs, all the assignments, everything that we covered in this project will be uploaded. It basically consists of 4 sub-steps. The first one is document ingestion. Basically, we load all the relevant course materials of our project. You load your source knowledge into the memory. If we consider a general case, all the PDF documents, let's say YouTube transcripts, GitHub repos, whatever we feel is important are uploaded. For this, various packages can be used. LangChain provides a bunch of them like PyPDF, Loader, GetLoader, etc. One of them is used in the final project that we are going to prepare. The next sub-step is text chunking. In this step, we basically break our large documents that we uploaded in the step of document ingestion into small, semantically meaningful chunks. Let's say this was the entire document. It is split into smaller chunks. Our LLM cannot handle all the tokens at the same time because it has a limit. So we basically divide it into smaller chunks so that it can effectively capture all the meaning. And we want to capture the semantic meaning of all chunks, right? We want to check out the semantic meaning of all chunks in the future steps. And it is considered that if a very long sentence is provided, like for a very large document at a time, if we process all the chunks, it's very difficult to capture the semantic meaning because each chunks might have different meanings. The third step is embedding generation. All these chunks that we prepared in the previous step are passed through an embedding layer. Let's say we want to convert all these chunks into vectors of 512 dimensions. So we obtain three vectors for our chunks. So in the step of embedding generation, what we do is we convert each chunk into a dense vector that captures its semantic meaning. We can use OpenAI embedding, Gemini's Gen AI package for doing this step. So we obtain vectors of 512 dimensions for every chunk. Now what we do is we store all these chunks in our vector database. Basically the original chunk plus its vector embedding, they are mapped and stored in the vector database that we defined. There are lots of libraries that can be used like Chroma, etc. If we draw the entire workflow of indexing, what happens is from internet, like a very large source of data, we load relevant data into our memory. Then we used a text splitter to split them into smaller chunks. Then we passed them through an embedding layer and we obtained dense vectors of certain dimensions. We defined 512 in our case. Now we store them in a database. This vector database acts as the external knowledge base for our RAG pipeline. Now comes the second step after indexing, which is retrieval. What happens in retrieval is, it is the real-time process of finding the most relevant pieces of information from a pre-built index. Here the pre-built index is the vector database that we created in the previous step. For finding the most relevant pieces of information, what we do is we use similarity scores like cosine similarity. What we do is we take the query, pass it through the same embedding layer and obtain a dense representation of our query. Let's say it's of 512 dimensions. The query is represented in the same dimension as the chunks that we kept in our vector database. So they should be equal. The dimensions should be equal. Now what we do is we take this vector. Let's define the chunks as C1, C2, C3. So what we do is we find the cosine similarity between all these chunks and our query. So now we obtained the similarity scores. Let they be S1, S2, S3. Now we rank them from top to bottom. Let's say this is the order. S2 has the highest similarity value, that followed by S3, then S1. Now we select the top k chunks. As the similarity of these chunks is very high, we consider them as relevant with respect to our query. The value of k can be defined by s. So if we consider 1, then only s2 will be added to the context. So overall what we do in this step is we find the embedding vector of our query. We do a semantic search. Semantic search can be done with the help of cosine similarity. We can also calculate the Euclidean distance between all these vectors. You can also use various hybrid strategies. The one I used in my project was I combined ChromaDB with BM25. Okay, you can look into that, what happened here. So we can use complex semantic searches as well, which are available. Then what we do is we rank them, like top k we can do. And then we find out the most relevant chunks and add it to the prompt in our next step, which is augmentation. So it is the step where the retrieved document, that is the chunks of relevant context, are combined with the user's query to form a new enriched prompt for the LLM. So writing it down, where the retrieval documents chunks are combined with the user's query to form new enriched prompt for the LLM. If we take an example of this augmentation step, the prompt, enriched prompt that we prepared for our LLM would look like: you are an helpful assistant. Answer the question only from the provided context. If the context is insufficient, Just say you don't know. Then we give the context, which we obtain from the top k chunks based on similarity scores. Then we finally ask our question, that is the query. This is how an enriched prompt would look like. It's an example. The final step is generation. So it is the final step where a large language model uses the user's query and retrieved and augmented context to generate a response. So yeah, this is the reason why we call it retrieval augmented generation. So these are all the steps that we did in our RAG pipeline. If we combine all these steps, let me add it here. After we prepared our vector database, let me copy it. We took the query, we passed it through the retriever, which did a semantic search over the vector database and obtained the most relevant chunks out of it. So this and this combine. So these are the relevant chunks plus the query. So they prepare the final prompt. It gives the prompt, and this prompt is passed through the LLM, which uses its text generation capabilities to produce the response. So initially we discussed three problems that our Vanilla LLM faced. We initially tried fine-tuning, but due to its computationally expensive nature, we tried to find a shortcut. Okay, we tried to find a simpler solution which won't involve the updating of weights. We used the property of in-context learning of LLMs, which arise due to its complex architecture, and developed RAG. So let's see how RAG solves the three problems that we discussed initially. The first one was of private data. So mentally, now if we have prepared ourselves that we want to ask about Amazon, like we discussed earlier. So what we would do is in the text digestion step, text ingestion step, sorry. What we would do is we would give all the documents of Amazon, like all its legal policies, the qualifications of their employees. Okay, so all these documents that are relevant, any project that the company is working on. So we pass all of them into our memory, and we carry out our next pipeline. So in this way, when we expect when we give a query to the LLM and expect an answer, the answer will be grounded to all these documents. The second problem was of knowledge cutoff date. So let's say if the knowledge cutoff date of our LLM was 1st Jan 2026 and we want the weather of 14th January 2026, what we would do is pass the recent weather report into the memory, and then our RAG pipeline would do the rest. It would split these new articles into smaller chunks and then store in the vector database, and then we would carry out semantic search with our query and extract all the relevant top K chunks with respect to the query. So in this way, the problem of knowledge cutoff will be solved. The third problem was hallucinations. So as we saw earlier, we took the bear example, right? Our query was, when did teddy bears rule us? So if you provide India's history as our memory, then this will be divided into chunks and stored in the vector database, which acts as our knowledge base. So when we make this query, our pipeline will give all the relevant context to the prompt which is passed through the LLM, and finally it gives out the correct answer, which is no, they never ruled us. So RAG helps our LLM to stay grounded. Popular applications of RAG include people practicing law. So what they can do is, let's say, as I said earlier, if you want to ask a question regarding Amazon's legal policies, what we would do is upload all the legal documents of that company. And like all the legal policies of companies are different, like they differ from each other. So we can give the company specific data to our memory. Also in medical field, we can use it. So these are some of the popular applications of RAG. So yeah, that's all. Thank you.